Hey everyone, and welcome to this explainer. Today, we're getting totally laser focused on mastering a really vital organic chemistry mechanism. You know, the secret to complex chemical synthesis? It isn't about memorizing every single thing at once. No way. It's about conquering it one reaction at a time. By the end of our time today, you're going to have a deep understanding of the Swarts reaction and exactly how this particular chemical transformation does its thing. Okay, let's just dive right into this. You see, the driving mission of SHREE-EDU-SPARK is igniting minds, shaping futures. And I really want you to keep that in the back of your head as we go through this today. Why? Well, because that spark of realization, that aha moment, that's exactly what happens when a complex reaction finally clicks into place. Really understanding these foundational building blocks, that's literally how we shape our capabilities, step by step. So let's frame up the chemical problem we're actually solving today. In the world of synthesis, you're constantly dealing with a starting material that, well, it's just not quite what you need for your final product, right? You need a reliable way to transform it. Our specific goal today? Creating a compound known as an alkyl fluoride. But obviously, we aren't just pulling it out of thin air. We need an efficient method to prepare these alkyl fluorides starting from other corresponding alkyl halides. That is the exact challenge our source material tackles. Like, how do we make that specific structural swap happen? Enter our primary solution, the Swarts reaction. Honestly, it's brilliantly straightforward. This reaction is used specifically to prepare alkyl fluorides from their corresponding alkyl halides. It just doesn't overcomplicate things. If you've got an alkyl chloride or maybe an alkyl iodide setting there and you absolutely need to swap that halogen out for a fluorine atom, boom, this is your exact chemical pathway. Now, what's really interesting about this is how beautifully clean the academic layout is in our source material. You've got that crisp, precise definition we literally just talked about, sitting perfectly above the actual chemical equations. I love this because it grounds you in the theory before completely plunging you into the practical application. You read what the reaction does, and then bam, you instantly see it proven right underneath in the formulas. It's just a top-tier piece of educational design. But before we totally decode those specific equations, let's take a quick second to look at the broader organic chemistry context here. You'll notice other compounds like benzene diazonium chloride and chlorobenzene kind of floating around. While organic chemistry is obviously this massive landscape of complex ring structures and pathways, our focus isolates the Swarts reaction as a distinct, standalone tool listed right there as item 29. It's a really great reminder that, sure, OChem is vast, but actually learning it requires us to zoom in and conquer one specific mechanism at a time. Section 7, Analyzing Halogen Exchanges. Let's move to and see how this builds. So our source material actually gives us two really fantastic, distinct examples to deconstruct here. Take a look at the first reaction pathway. We're starting with two molecules of ethyl chloride, and we're reacting them with mercury 1 fluoride. Now shift your focus to the second pathway. Here, the starting alkyl halide is completely different. We're working with ethyl iodide. And guess what? The metallic fluoride we're using to react with it is different too, silver fluoride. So we basically have two entirely different starting halides and two different metallic fluorides being utilized to kick off the exact same type of reaction. So the crucial point here is that despite the different specific chemicals being used in those two equations, the overarching mechanism happening in both is identical. We can actually break it down into three universal steps, pulling directly from our source. Step 1, start with an alkyl chloride or an alkyl iodide. Step 2, react that compound with a metal fluoride, like the mercury or silver compounds we just looked at. And finally, step 3, you yield your alkyl fluoride. At its core, the Swarts reaction is just this wonderfully straightforward swap. The halogen that was originally attached to the alkyl group gets traded out, and the fluorine from the metal swoops in and takes its place. And that brings us to the final payoff of our equations. Notice anything? The primary product in both of these pathways is exactly the same, C2H5F, or ethyl fluoride. So, whether you started with a chloride and mercury or an iodide and silver, we successfully achieve our exact initial goal of creating an alkyl fluoride. Of course, the swap means the leftover pieces have to go somewhere, right? That leaves behind our byproducts. We get mercury 1 chloride in the first one and silver iodide in the second. The chemistry is perfectly balanced and the objective is 100% achieved. And honestly, this brilliantly illustrates the real beauty of structured learning. Mastering a specific, highly detailed chemical reaction like the Swarts reaction isn't just about rote memorizing letters and numbers.
It ties directly back to that aspirational mission we talked about at the start, igniting minds and shaping futures. Every single time you lock down a foundational concept, every time you truly, deeply understand how one molecule transforms into another, you're building the intellectual toolkit you're going to need to tackle even bigger scientific challenges down the road. You are quite literally shaping your own capability for the future.
Which brings me to this final thought I want to leave you with today. We've seen exactly how alkyl fluorides are prepared from their corresponding alkyl halides. We've broken down the metallic fluorides, we've looked at the halogen swap, the whole shebang. So I've got to ask you, how will mastering the foundational reactions, like the Swarts reaction,